All right, so today we're going to be starting on the last module for this course, and we'll be focusing. This will be our focus for the next 3 weeks. It's about trees and tree-based data structures. Trees are essentially just a very special case of generalized graphs, and we will use them to exploit them and their structure. In fact, that's why we like data structures, right? The whole reason that we do data structures is for the structure, right? We like data structures and algorithms, because structure can be exploited for efficient operations, right? And to motivate this, remember we are on YouTube, so if you have any questions, you can post to the live stream, or you can post to Piazza here. Anyway, let's think about what we've already done so far in this course, and think about their structures and how we've exploited them in order to have efficient operations, right? Basically, our motivation is that we want a data structure that supports efficient CRUD, right? Create, retrieve, update, and destroy, or retrieval or search, right? Insertion, in other words, putting stuff into the data structure, and deletion. Now, CRUD, there's also an update there, CRUD, but that the update is simply just a pull something out and then and delete it and then replace it. So the U can be achieved by one of these other two basic operations. So structure. So we've looked at lists, right? What about linked lists? Linked lists. So now that we have some algorithm analysis, big O analysis, now we can start couching this this in terms of big O complexity, right? What about the time for insertion or deletion, right? From the head or tail of a linked list. How would you characterize that? That's going to be order what? Remember, we're only suppose that we're keeping track of the head and the tail in this implementation. To add something to the head of the list means that you're simply creating a brand new node and linking it to the pre-existing list. So is that going to be quadratic? Is it going to be linear? Is it going to be exponential? Or is it going to be what? Constant, right? In other words, order 1, right? You could say order 42, right? But why? Just 1, right? 0 doesn't really make any sense because that means that it doesn't cost you anything at all. So we're going to go ahead and keep it as constant, right? So this is a constant time operation. Now on the flip side, a linked list, if you wanted to do an arbitrary insertion or index-based find or search method, then that would end up being what? Insertion. There we go. So what if I wanted the thing right in the middle of a list and there were a million things in there? Can I just jump to that location? No, I have to start at the beginning and do 500,000 traversals to get to the center of the linked list, right? So order 1/2 n, and when we ignore lower constants and lower order terms, we have it's linear. Okay. Now, flip that. If we add an array-based list, then what about the insertion or deletion from the start or end, or let's just go with start of the list, right? What's gonna be the complexity now? So if I've got a million things in there and I want to put something at the very beginning, what do I have to do to those other million things? Shift them down. Right? And then I make room for that one element. So it's just the opposite here, right? Something that was efficient, constant time operation on a linked list now becomes a linear time operation on an array-based list. And what about an arbitrary index-based search? We won't worry about the insertion here, but what about an arbitrary index-based search? If you want the element at index 42, right? Do you have to start at the beginning and go over 42 elements? Nope. You have random access with an array. so you can immediately jump to that memory location. It might involve a cache miss or something like that at a lower level, and that has to be loaded up in memory or something like that. But don't worry about that. From the perspective of a high-level algorithm, it's going to be constant time. Right? So these two situations are exactly flipped. What we actually want, though, is I want everything to be efficient, right? And so we need some more work here. Well, there is one instance where we used a list that everything was efficient. What about a stack or a queue, right? The push and pop operations were both order 1. They were both order constant time algorithms. Why? Because, but, it comes with a caveat here, both stacks and queues were restricted access data structures. The structure was not in how they stored things. You could do it within a linked list or an array-based list. It was not how they stored things. It was how you interacted with the data structure itself. You could only work at one end to pull something off or put something on, right? Or you could work at both ends and then you've got a deck, right? Or you just have to be consistent about it. Work at one end or another end and you've got a queue, right? But those are restricted access data structures. The idea was we're not going to allow arbitrary access. We're only going to allow access at one end of the queue or both ends of the queue or to the deck or whatever. And in that structure, by limiting the behavior, the interface, that's how we achieved efficient time operations here, right? What's another situation? What about searching an array or an array-based list or array-based list? Right? What's another way that we can impose an ordering on an array to do efficient searching? Is there a difference between an array that is sorted and an array that's randomized? What if it were sorted? If sorted, we can use what? Binary search or B search to have order log n search operations. Now, if I want to insert something at a particular location and I use binary search to find out where it should be, right? That still means that I have to shift stuff down. Can we use binary search on a linked list? No. Well, how does binary search work again? You jump to the middle and then determine, do I search in this half or do I search in this half? Can we jump to the middle with a linked list? Nope. So we're kind of stuck here, right? We need something else, right? Our ultimate goal is efficient operations for all operations, right? Now, we're not going to get there all the way there in this class, but we are going to get most of the way there. The idea here is that we're going to start using a different data structure called a tree, right? Trees provide an opportunity, a potential for efficient operations. Now, by the end of the day, we will understand that potential. It's just that by the end of the class, we will not reach that full potential. You need what are called balanced binary search trees. That's just a preview, though. All right, so let's talk about trees. Right? To talk about trees, we need to first talk about graphs. A graph is a now this is not a graph as in like X, Y axis, and then you're graphing something. It's a graph as in it's a collection of nodes, nodes, or vertices. Generally, we call them, in graph theory, we call them vertices. In computer science, when we use them as a data structure, you're storing something in those nodes, and so that's why we call them nodes. Right? It's just a little bit nuanced, right? And edges, connecting nodes. Here's an example. There's a graph. What are the nodes here? A, B, C, D, E, F, G. In other words, there are 7, I counted, 7 nodes here. These edges connect between those nodes. For example, A is connected to F. Now, is A connected to C? No. Otherwise, there would be an edge there. Don't read anything into the crossing of edges. That's just so that they can be for presentation purposes. This intersection here of these two edges is meaningless. You can think of it in terms of 3 space. Like if you've got these two things that are intersecting, fine. Just go ahead and go up another dimension, and now they're not intersecting, right? They're overlapping, right? There are 7 nodes here. How many edges are there? I count 1, 2, 3. 1, 2, 3. 1. Do I count that again? Nope. 1, 2, 3, I think. And then 1, 2. So that was 11? I'm not sure. I lost count. But each one of these is an edge, right? They're connecting nodes. You can also have paths. For example, we said that A was not connected to C because there's no edge there. But can you go from A to C in this graph? Sure. Go from A to F, and then from F to C. Right? That's a path. Or another path would be that you could go to A to D, then D to F, and then over to C. The length of those is the number of edges along that path. So if you want to consider this path right here, where you're going from A to D, to F, and over to C, that is a path of length 3. If you went instead from A to F, then that's a path of length 2. You can talk about immediate paths of length 1 if you want to, and that's perfectly fine. Is there a path of length 1 from A to C? No, because they're not connected. Okay? So this is what we mean by vertices or nodes and edges in that graph, right? A tree is an acyclic graph, right? That is a graph with no cycles. What does that mean? Let's come back over here to this example. And is this a tree? Right? Well, for that, we need to know what is a cycle. Well, remember, I could go from A to B to D to F, right? Is that a cycle? No, it's a path because you start at A and you end up at C. That's a path. What if you started from A, went to D, over to F, and then went back to A? That is a cycle. Why is it a cycle? You start at a node, you traverse the graph or whatever, and then you come back onto that node. Right? A cycle is a path that ends up at the same node at where you started. Now, from the perspective of this graph here, where did you actually start? Right, if I just drew the cycle like that, and it's a cycle of length, what? 3 vertices along it, right? And it's a cycle because you end up at where you began. Now, did I begin at A or D or F? Yes, right? That's all the same, right? There's no orientation here. That if I go from A to D to F, that's the same thing as starting at D and then going over to F and then back to A. Or F going to A to D, right? Or reverse all of those, right? There's no orientation here. It's not a directed graph, and we're not going to talk about directed graphs. But it doesn't matter if you're going around this way, clockwise, or going around counterclockwise, or whichever one. There we go. Counterclockwise would be that way. There we go. All right. Erase all my mistakes. There. So you can have FDA or AFD or DAF, etc., etc. Right? All of those are the same cycle. So this graph does have cycles, right? In fact, there's one cycle. What's another cycle? Of different length, say. If I go from A to E to G to D and then back to A, that's a cycle of length 4, right? 4 edges there. Is there an even larger cycle? 1, 2, let's see, 3, 4, 5, nope, 5, 6. There we go. Yeah, there. There's a cycle of length 6. Right? So is this a tree? No, because it has cycles. Right? Remember what the definition of a tree is. A tree is an acyclic graph, a graph with no cycles. Okay. Again, I implicitly gave you the definition here, but what is a cycle? A simple cycle is a path in a graph that begins and ends at the same node or vertex. Right? The length of a path or cycle is the number of edges along that path. The way that you think about this is that if you want to traverse the graph, just like a linked list, if you want to go from node A to B to C, how many traversals do you need to go? If I'm already at A, it's not going to cost me anything to stay there. But if I'm going to go to B and then C, how many jumps did I make? 2, right? And that is that corresponds to each edge along the way here. Okay. Now, what do we mean by a simple cycle? A to D to C, A to D to F over to A, right? That's a simple cycle. Here's a more complex cycle, right? What if I went from A to E to B and then back and then back and then back and then went over there and then over there and over there, right? That's also a cycle because it is a path that you start at A and you ended up at A, but it's not a simple cycle because I traversed the same edge more than once, right? So a simple cycle is the path or that you end up at the same vertex without traversing the same vertex or edge more than once. If you do that, then just take that out and you've got a simpler cycle that has the same topology. Topology being the shape of a graph or the shape of a path in a graph or something like that. Okay? All right. And again, what is a path? A path, I should have put that first actually, right? A path in a graph is a sequence of connected vertices, right? So for example, is it a valid path that I go from, say, is ACF? Is that a valid path? Can I go from A to C to F? No. I can get to F, right? And in fact, I can get there through intermediary vertices. But this is not a valid path right here, okay? All right, now that we've got that terminology down, let's see, what else do we want? A tree may be connected or disconnected. Right? A disconnected tree is a forest. Right? So what do we mean by that? Let's go ahead and take a look at an example here, and I'll just draw examples from now on. Right? So if I've got a tree here, A to B to C, D, E, F, and G, let's say. All right, now, first of all, is that a tree? Yeah, I've taken, are there any cycles there? No. Now, you might say, well, you could go ahead and take a path that goes from A to B to C, and then back to B, and then back to A. Is that really a cycle, though? No, because it's not a simple cycle. And we're only going to restrict our attention to simple paths and simple cycles, okay? If I had put something like this over here, right? Now, is it a tree? Nope, because it has a cycle, okay? Now, that's one tree, right? Where did I leave off? G, H, I, and J. There. There's another tree. And if I consider both of these components as one graph, then it's a disconnected tree. Because there is one component that I can't reach to another component. From A, I can get to any vertex in this entire tree here by simply just traversing some path. But I can't, if I start at A, there's no way to get over here to H because it ends up being disconnected. That's okay. What do we call one tree, two trees? A forest. We don't call it groves. We call it groves, right? A forest is very large, but the one for computer science, a tree, once you have two of them, you have an entire forest, right? There's nothing in between. There's not an arbor. There's not a grove, whatever, right? Or anything like that. All right. So that is the basic definitions. Now let's go ahead and talk about binary trees. You can generally orient trees downward. Oops, sorry. Go back over here. Right? I read it out loud anyway. So what do I mean by that? Well, let's go ahead and look at an example here. Let's see, what kind of tree do I want? Nope, I'll go ahead and go with my own tree here. All right, let's go ahead and get rid of this other tree over here so that we only have one tree. Okay. Now imagine that this was in 3 space, and maybe that I grabbed the node C, right, and then I lifted it up, right, and then I used gravity to shake it, and then all the nodes dangled down. What would it look like then? Right. Well, C is connected to B. What else? I'll go in order here. D, E, F, and G. There we go. Those are all the nodes that it's immediately connected to. So if I lifted that out of my tablet here and I shook it and I let everything fall due to gravity, then it would look something like this. Now, of course, I've missed what? A. A is now hanging off of B. That's what it would look like if I pulled it up by C. What would it look like if I pulled it up by A instead? A would be at the top, right? And then B would be dangling below it. And then B, from B we can get to, what is it, C? Right. And then all of the other 4 vertices that are dangling off of C, then they would all be down here. What is it? G, or D, E, F, and G. Right. That's just a different orientation. You can imagine what it would look like if I pulled it up by D or something else, right? What would I have it with D? D, then hanging off of that would be C, then hanging off of that would be B, E, F, and G, and then hanging off of B would be A. Something like that, right? That orientation is a top-down, right? And up here, unfortunately, we call it the root. It's not like a real tree. Where's the root in a real tree? It's down, right? And up here, we've got the leaves. But in a computer science tree, the root is at the top, and all of our leaves are at the bottom. They grow downward. Why is that? It's because of Cayley 300 years ago. The person who created, or who started using these data structures in the mathematical context, and he just made all of his trees grow down. Why? Because we, at least in English, or in most Western languages, we like to read top to bottom, left to right, right? And if we're going to be storing stuff in our nodes, this is data that we want to read, this is data that we want to visualize. And so we want it to be read top to bottom, left to right. And that's why our trees grow downward in computer science, right? All right, so with an orientation, you can generally orient trees downward. At the top is a single node called the root, right? You have this induces a parent-child relationship, right? So this is nothing new. If you've ever looked at like a family tree, family trees generally grow downward as well, right? So we've got the parent up here and the child down here. I have seen family trees that they grow upwards instead or whatever. But most of them that I've ever seen are going to grow downward. We've got ancestors up here, and we've got descendants down here, and we do use that terminology with respect to trees as well. Okay. All right. So you can not only that, but you can also orient nodes in a left to right manner. In fact, we did that implicitly over here. Right? I was very, very careful to list all of its children, right? Here's a parent, here's all of its children. I was very careful to list them in alphabetic order, left to right. Right? It doesn't really matter. If you switch these two around, it's going to be the exact same topology. It's going to be the exact same shape. It's just that you're reading out of order now, right? So it makes sense to have a parent-child relationship and a left to right relationship. Okay. Now what we're going to do is we're going to further restrict and add more structure to this data structure. Right? A further restriction. suppose that a tree is only, the tree node is only allowed at most 2 children. Right? In other words, it can have 0, 1, or 2 children. Right? It's still allowed to have no children. It's still allowed to have 1 child. And it's still allowed to have 2 children, right? There are 3 options there. This is a binary tree. Now, why do we call it a binary tree? 2, right? At most 2 children, okay? Are any of these orientations that I drew a binary tree? Nope, because C necessarily here has 5 children. B only has 1 child. A only has 0 children, right? So those would conform to the definition, but C here does not conform to the definition. So let's draw a brand new tree that is a binary tree. A. I'll make this have 2 children, B and C. I'll make this one have 2 children as well, D, E. But what I'll do is I'll make this one only have 1 child, E, F. Right? And I'll make this one have 1 child, G. And I'll make this one have 2 children. G, A, B, C, D, F, G, H, I. Always have to sing the alphabet because I forget it. There we go. All right. There's a binary tree. Right? If you look at particular nodes, A, B, and E, they all have 2 children. Right? If you look at other nodes, for example, E and D, they only have 1 child, but they have a different child. Right? In general, what we have is a parent, left child, and a right child. Remember, you can orient them to left to right, and so it makes sense to have a left and a right child. D here has a right child, but no left child. C here has a right child, but no left child. Right? So it's possible to have one or the other or neither or both. Right? 4 possibilities here. So we can start making some observations here or adding some more terminology, right? Depending on how many children it has. Right? In a binary tree, you can have a left child or a right child or both or neither. Right? You can also have a parent. Right? So if a node has no parent, it is the, what did we call that thing again? That thing at the very top with no ancestry at all? Where does a tree begin? At the root, right? Is the root of the tree. And by the way, we're talking about connected trees now. We're not talking about forests anymore, right? If a node has no children, it is called a... So no children would be something at the very bottom here. F, G, H, and I, they have no children. So if the tree begins up here with the root and ends down here, what do we call these things at the end of the tree? Leaves. Right? Their leaf is called a leaf. Okay. Let's see. We also have some more definitions. Given an orientation of a tree, you can talk about the depth of nodes. For that, let's just go ahead and go over here and start talking about the depth. What is the depth? It's the path from the root node down to that node. Right? So, for example, depth. What about B and C? Or here, I mean, oh. All right, I don't know why we lost that, but sorry. That's only affecting those on in here. There we go. Sorry about that. All right, so here's the node. And what is its depth? So the node B here, that's right there. How can I get here from the root node? With a tree traversal, just like a linked list, you have to start at the head, or you can start at the tail and work one way or the other way. Right? With a tree, however, you need a starting point, and the starting point is always going to be the root. If I start out at the root and I need to traverse to B, how many steps did it take me to get there? 1, right? There is a path of length 1 from A to B. Right? The length of that path is its depth. So 1. Right? Why do we call it depth? Because we start at the top. Right? This is the top. And again, trees are reversed in computer science. And this is the bottom. So if I'm going to traverse from the top to the bottom, right, then I need to make a certain number of steps, etc. All right, well, what about C? Likewise, that has a depth of 1. What about the rest of them? D, E, F, G, H, I. What is the depth of, say, D? Well, there it is. From A, from the root, how many traversals did I need to get to there? 2. And because of the way that I drew this, with everything at equal depth being on the same plane, on the same level, right? E and F, they're going to have depth 2 and 2 as well. Okay? What about G, H, and I? They will have depth what? 3. One that I left off here was the root node. By definition, what is the depth of the root node? It's the length of the path going from A to A. Well, what's the length of the path if I'm already at A? Do I go anywhere if I want to be there? No. You just stay there. So what's the depth? 0 by convention, right? And by definition. So the depth of a node is the length of the path from the root to the node U. Let me go ahead and say path of a node U is the length of the path. There we go. That's what I wanted. Okay. The depth of a tree itself is the maximal depth of any node. Right, there we go. So, in this example, what is the depth of the tree itself? Depth of T. I'll just call this T. It's going to be what? 3. Why? Well, just look at all these depths over here and take the maximum, right? And that's the maximum depth. How could I make this tree even deeper? Well, I could add a child over here. Would adding a child to C, would that make the tree deeper? No, right? Because it's higher up in the tree. Right? Again, you have to orient it with respect to how we draw it, not to how trees actually grow. So the depth of this tree is 3. Let's make another observation. There you go. Copy. Paste. Got a clean tree here now, right? So question, how many paths from the root A to any other node exist? Right. So let's just take a node. Right. E. How many paths are there from A to E? Well, I see 1. Is there another path besides that one? No. What if there were? What if there was another path that went back over to A? Guess what? What do we have now? A cycle, right? So, 1, always. There's our structure that we're going to exploit, right? So another observation here is that since trees are acyclic, in fact, this is true for every vertex, from one vertex to any other vertex, there is exactly one path. Right? They're not 0 paths, because if there were 0 paths, we would have a disconnected tree. There's not 2 paths, because if I had 2 independent paths, then I would have a cycle. Right? Likewise, there's not 3, 4, 5, whatever, because those all would induce a cycle as well. Okay? All right. So, now, how can we exploit this structure? Question mark. Right. If we generally, we will store data in each node in some manner, okay? Our operations will always begin at the root and say search, insert, or delete, right? Will require traversing from the root to any descendant node. Right? That sounds mighty familiar, right? What if, for example, I were to get rid of, say, the left child of A? What do I have now? I still have a binary tree. It's just that everybody only has one child. We've seen that before. What is it? What if I were to take this thing and reorient it? Cut. Come on. Paste. And what if I were to move it like that, and then also give arrows to these things? What is that thing? It's a linked list. Exactly. So what's the difference between a tree, a binary tree, and a linked list? Instead of having one next node, what we're going to have is a left and a right child. Sometimes one or more of those will not be there, but other times they'll both be there. Right? It basically takes and allows us to take this really long linked list, right, and condense it down into a little bit more compact, but with some structure. Right? Just as with a linked list, if you start at the head and go to any other node, there's exactly one way of doing that, right? You start at the head and you go all the way over, right? There's not two paths. It's still acyclic. Likewise, with a binary tree, right, then there's still only one way to get from the root node to any other node. It's just a little bit more compact. How compact, right? So I'm going to go ahead and draw this dummy tree where I've got every single vertex, every single node present in it. Right? So here's my depth. At depth 0, how many total nodes at depth? So if I just draw one node here, right, then I only have, with depth 0, then I only have a root. Somebody suggested a couple years ago that we call that a seed, right? If it's only a single node tree, fine, it's a seed, right? But now let's look at depth 1 here. And what I'm going to do is I'm going to maximize the number of vertices or nodes that I have at each one of these depths. And that's maximized when you have both children at all depths all the way down. So 2 nodes at that depth, okay? At depth 2, we have how many nodes? If I have every single node having every single child? 4. Do that again. 1, 2, 3, 4, 5, 6, 7, 8. So at depth 3, I've got 8. ... What if I'm at depth, in fact, I'll go with depth D here. 2 to the D. Right? There's the pattern. Why? Because every node has 2 children. So if you have X nodes and they each have one child or 2 children, then you have 2X, 2X, 2X. In other words, it's a power of 2. Right? ... Right? What if I said that, now what I will do is I'll change this over to K. Right? 2 to the K. There we go. What if I said, all right, well, fine. Your depth of the entire tree, of this big giant tree here, is, say, D. How many nodes do I have at that depth? 2 to the D. Right? Now, what is the grand total here? What if I add all of these up here? Total. The grand total. 1 plus 2 plus 4 plus 8 plus ... That's going to be a summation of K running from 0, y0. We start at depth 0, all the way up to D, right, of 2 to the K. Again, this was 1 plus 2 plus 3 plus, or 3, 4 plus 8 plus ... 2 to the D. Now, does that that's a series now, right? It's a summation. It's a finite series technically, so it's a summation. What is the solution to that thing? Yeah. 2 to the d plus 1 minus 1 down here. Right? In fact, you can generalize this. It's going to be if this were like say x, then it would be something like x to the d plus 1 minus 1 divided by x minus 1 or something like that. Right? I forget what it is. But there's a general form solution for this, and it turns out that if your base here is 2, because of binary, right, binary tree, then you end up with this this closed form solution here. Right? So why is this important? Well, suppose you had n nodes in a binary tree. Then just the opposite. What is its depth? What is its depth? Question mark. Right? Again, I'm going to restrict myself to this full tree where all the children are there. Okay? In other words, n is equal to 2 to the d plus 1 minus d. So the question of what is its depth is simply just taking this equation and solving for d. Okay? So, I don't know if it's quicker to copy and paste or to rewrite it. There we go. Solve for d. Help me out. We've done this now a couple of times when we've looked at, say, binary search for analysis, right? It's easy enough to take 1 onto the other side, sure. 2 to the d plus 1. Right? Now, how do I get rid of that 2 to the? Take log base 2 of n plus 1. But remember that you are a self-respecting computer scientist, so you do not write 2. All our logs are base 2 implicitly, right? Is equal to d plus 1. Okay? Take the 1 onto the other side, and you have that d is equal to log base 2 of n plus 1 minus 1. Right? That's order what? Ignore order terms, the minus 1, the plus 1 even in that log, and you have what? Log n. That looks familiar. Binary search, right? That's the same as binary search. Right? And it's no coincidence. Take a look at, say, an array. Do I have an array here? I'll go, there we go. Right. Here's my array. Oh, that's not sorted. I want a different one. Let's go with this. Is there a sorted array? There, sorted array. Okay. Now, if this were an array and you stored things here sorted, you could jump to any location, like I'm doing, say, with binary search. I'd jump to the middle, right? You can't do that with a linked list data structure, and you can't necessarily jump to the middle in a tree, or can you? If I were to, say, have this ordering in my tree, what would it look like, potentially? What if I take this and I promote it up to be a root, 12? Right? Now I've got this left part here and this right part here. What if I did the same thing and took the middle element and promoted that up to be a child, and take this middle element here and promote that up to be a child? 4 and 102. Right? Likewise, what are the two children of 4? It doesn't really matter. 2 and then negative 3. And then 4 and 9, something like that, right? And then over here, the same thing. We'll just go ahead and make 42 the root, and then 34 over here, and then 157 and 180. Not all the children are there, but that's the same basic structure, but without an array. Now, what does jumping to the middle look like? You start at the root. The middle is the root. The root is the middle, right? Now, what about traversing to the left part of this for binary search and you wanted to jump to the middle of that? It's right there. You're always defining the root as the middle of these things, ideally, right? And that's why if you can magically jump to the middle, you can get this logarithmic behavior. If you can magically jump to the middle of a tree, which is its structure itself, then you might have the same ability to exploit it and get logarithmic behavior here. So the observation in a full binary tree, the depth is logarithmic. Right? Order, D is going to be order log n. There we go. Right? If, and that's a big if, we can make all operations, that is, inserting stuff, insertion, deletion, and search, proportional to the depth of a tree, then we've achieved our goal, right? That I can have efficient operations, logarithmic operations for everything. Not just, oh, well, in one situation, right, it's going to be efficient and it's going to be constant time. In another situation, but unfortunately, it's going to be linear, so we'll pay for it, right? Here, I'm offered the opportunity to have logarithmic behavior for all of these things, if I can come up with a way to do it. Right? You do have to be careful, though, right? It also requires that the depth, or that the tree, be nearly, at least nearly, full, right? You can have a tree, oriented tree, binary tree, that is not full, right? We kind of call these skewed trees, right? For example, let's go ahead and go back over here to my diagram, and let's draw a skewed tree, right? 10, 20, 30, 40, 50, ... down to 100. All right? How many nodes are there implicitly? 10. So what's the depth of this tree now? 1, 2, 3, ... Now there are 10 things, so in between 10 things there would be 9 edges, right? So the depth of this tree is going to end up being 9. In general, a tree can have depth order n if it's skewed like this. Now remember, what is this? This is technically, I mean, the way that I've written it here, it's a tree because it's oriented, it's binary tree. There's at most two nodes, right? In fact, here there's at most one node. We call that a what? That's a linked list, right? So it is possible that your tree degenerates into a skewed tree, and that it is that it's not going to have depth that's logarithmic. Right? That's the missing piece for this course. We're not going to be able to get to a point where we can ensure that it doesn't look like this, but we're going to try. All right, we're going to get halfway there. Okay. Before we do that, though, we need to talk about more structure. All right. So remember that we said generally we store elements in a tree node, right? You can also impose additional structure on that data, that it be ordered. Right? And this leads to what's called a binary search tree. Right? In a binary search tree, all nodes have a key element, right? And I'll just call it K. For every node, the key value of all nodes in its left tree, subtree, I should say, subtree, have a key value strictly less than K, subtree, let me do it like that. And for every node, the key value of all its nodes in its right subtree have a value that is strictly greater than K. Now let's visualize that. Let's go ahead and suppose that we have a node here, and in that node we have a key value k. For our purposes, we're just going to restrict ourselves to integers. It really doesn't matter because you can always come up with a hash code that you can take your student object or your account object and translate that into an integer value. Right? Here's my value k. This is the left subtree, and it might have like 50 nodes in it. It might have 10 nodes, whatever the structure is, whatever the topology is. But whatever the topology, everything over here is strictly less than k. Everything over here in the right subtree is greater than k. Right? So this is the right, and we call it a subtree because it's not necessary that this has to hold for all nodes. This could be a child of some parent up here. Right? It is possible. It could be a left child or it could be a right child of some parent up here. We're only focusing on the tree rooted at k. Right? Everything in the left subtree, and this is the left subtree, is going to have a key value less than k, and everything over here is going to have a key value greater than k. Now, naturally, what kind of restriction did I put on this? I can't have any duplicates, exactly. Right? So what if you want duplicates? Okay, well, you just need to be consistent about it. Do you put it down over here, less than or equal to? Okay, fine. Right? But you can't have both. Less than or equal to and greater than or equal to. So you can loosen this definition up to allow duplicates by simply saying, well, ties go to the left, or ties go to the right. Right? That's just a small implementation detail. For us, we're just going to say, oh, no, you can't have duplicates for now. Okay? Why is this nice? Let me go ahead and give you a full binary search tree. Go back to your science 2, trees, down here. Come on, and binary search trees. There we go. There's a binary search tree. You can verify that by looking at each one of these key values. 50. Look at all the key values in its left subtree. You observe that they are less than 50. Everything over in the right subtree is going to be greater than 50. Right? That's also an inductive property. If you look at any other node, 20 here, everything in its left subtree is less than 20. Everything in its right subtree is greater than 20. Right? It has to hold for all nodes. As another example, let's go ahead and put this, here we go. All right, I'll put this above this. There we go. All right, lexicographically, is that a binary search tree? Is everything over here less than A? No. Right? Is everything over here greater than A? Well, yeah, but just by coincidence. Okay. So this is not a binary search tree. It is a binary tree, though, right? What's the depth of E? 1, 2. What's the depth of the entire tree? Well, you can see here that R is going to be the deepest node. 1, 2, 3, 4, 5. So the depth of the tree here is 5, right? How many nodes? I'll let you count those up. If I had, say, 10 nodes, how many edges do I have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I can do it in my head without counting them up. How many edges am I going to have? Exactly 17 in this case. Why? If I had n nodes in general, then to connect all those things together without inducing a cycle, how many edges do you necessarily have? N minus 1. Right? If you have n nodes, then you have n minus 1 edges. Exactly. Right? That's just another property. It won't come into play in our discussion here, though. It's just another interesting property if you want. Okay? This suggests that we can exploit this structure. What if I wanted to search for 49? If this were binary search, I would jump to the middle of the array, and I would say, oh, I want to search, what did I say, 49? Right? 50, that's not it, right? Oops. That's not it. So where do I search? I search in the left part of the array. Same thing with a binary search tree. Is there any point to going to the right part of the tree? Nope, because everything over here is greater than k. Right? So it's a way that you can have your cake and eat it too. You don't have to store everything into an array where you have to shift everything down, right? Just to insert something at the beginning. But also, it allows you to exploit this binary search tree property, right? That you can go ahead and go left, and ideally, you can cut the tree in half and reduce your search down to logarithm, right? Same idea as binary tree, binary search, binary tree. Right? We're not there yet. Okay? So that is the structure that we want to exploit. Before we go on exploiting our structure, let's go ahead and think about how we would actually implement this in real life, right? Up till now, it's just a bunch of pretty pictures or ugly pictures, depending on, right? What about an actual implementation in, say, Java? What would that look like? Right? Well, it would look like kind of like a linked list in that, what do I have? I have a bunch of nodes, right? But it's not a node in that it only has one next. It has orientation. It has a left child and a right child. So let's go ahead and use that. Right? Use the same idea from the linked list, but instead of a list node, it will be a tree node. And what was the trick that we learned very quickly once we'd created a tree node? Or once we'd created a list node, we thought, well, wait, why is this an integer list node? I should be immediately parameterizing this so that it can hold integers, or it can hold doubles, or it can hold strings, or it can hold whatever, right? Immediately, you need to parameterize this to make it general. What does this hold? Does it hold doubles? Does it hold integers? Yes, right? To all of those things. All right, so we need to hold the actual data. So I'll make it private. And it's going to hold an element of type T, and I'll call it item. Right? That's the item that it's actually going to hold. If you want to, you can call it key. Or you can do key nodes separately. Or you can have the piece of data and then its key. Right? I'll just go ahead and keep it as just the piece of data and variations that we looked at. Right? You know, and it went on and on and on. Right? Sometimes we thought, well, this means that you can only go one way. It's a one-way linked list. Right? We thought, well, what if we were able to go back as well? Right? We had a next and a previous, and you were able to go back, right? So that you could traverse both directions. Might we want to traverse both directions in a tree? Given this node right here, I could go to the left child, I could go to the right child, but I could also go to the, what do we call this thing? Oh, that's the root in general, but with respect to 40, it's 40's parent. Right? Maybe I want to traverse in both directions. If so, go ahead and add another tree node. Call it parent. Right? There we go. Okay. Source, generate getters and setters. I'll just go with all the getters. Okay. All right, that'll be nice. What else do we want? A constructor probably. Source, generate, constructor using the fields. I'll go ahead and deselect all these things. I'm just going to go ahead and create a node item here, and then have then I'll let you, take care of the left-right topology or whatever, right? And that means that I should have generated the setters, right? So, source, generate setters. Select all setters except for the item. Right, I'll make that final. So why did I design it like this really quick? You can create a node with a key. That key does not change. But you can move the node around. Change its parent. Change its left child. Change its right child. Okay? If you need to, if you want to. All right. And I'm ensured that by making it final. Now, does that define a tree? No, that's just one node, right? A tree can have one node, two node, 3, 4, 5, n nodes. And I connect them all together somehow. So what is my definition of, say, a binary tree? New class. I'll call it binary tree. And I will also parameterize it the same as I did this one, because it could be a binary tree of integers, it could be a binary tree of doubles or strings or whatever. Do I keep track of all of the tree nodes? All nodes. No. In fact, that tells you what I'm doing here. I'm regressing back to an old data structure, a list, a linked list or an array-based list. That's not how it works. All our operations will start at the root. So I keep track of the root, which is a private tree node. There we go. I don't keep track of all of the nodes, because if I kept track of all the nodes, you'd have a list, right? And now you're back at square one. Maybe I do also want to keep track of some other things, just like I did with some tricks with the lists that we implemented, the linked list in particular. Maybe I want to keep track of the size, the number of nodes in the tree, so I don't have to recompute it every single time, right? Et cetera, et cetera. Right? And there's your tree. Right? Let's go ahead and build a tree now. In fact, let's build. That one's too big. Let's build the following tree. Where's my old tree? The small one that I made. That's too big. Okay, fine. Let's build that tree. At least part of it. Okay. Tree, or binary tree of t. My tree equals new binary tree. There we go. I actually have to put stuff into it. So we were putting, say, characters in here. I'll go ahead and just say it's strings, though, to make it easier. Right. So this is going to be a binary tree holding a string values. There we go. Right. Now, it's going to be some work here to actually, get this done. But my tree dot root should be equal to a new tree node. What was that? My root? A. So the item that I'll pass in there is A. Okay. Well, that's because of the visibility here, right? All right, so let's fix that, and then we should be okay. Should I change the visibility of the root here in binary tree to be public so that I can do this? Probably not. Come back here and let's go ahead and create a constructor here. And no, deselect all. I don't know. Let's go ahead and select the root, I guess, maybe. No, I'm going to go ahead and do it this way and then go a third route here. Item. Right? In fact, I'll call it root item. So if you create a brand new binary tree, you have to give me at least one element here, the root node. Right? And I'll go ahead and take care of that for you. This dot root is equal to new tree node, putting in that root item. There we go. What is your problem? This dot root, private. Huh? Did I? New tree node t. It's public. How is that constructor not? Oh, okay. It is not visible. I wasn't believing you. Sorry. I should have believed you. There we go. Because I didn't write it. Apparently that was the default when I generated that code. Right? In any case, we can go ahead and now pass in A. Oh, now you're not public either, are you? Yep. Public. There we go. Now everybody's happy. What does the tree look like at this point? Does it look like that thing? Nope. All it is, oh, good. What did we call that again? It's the seed, right? It's the seed of a tree. So let's start growing our tree. I will create another tree node here. Tree node of string. And I'll call it B. I'll literally call it B. Is equal to new tree node. Infer the type with the value B. There we go. And I'll do the same for C, D, E, F, G, H, I, J, C, D, E, oops, E, F, G. That's all I want to do. That's good enough. C, D, E, F, and G. There we go. And now I need to create the topology that we had over here. Okay? This is a really manual and tedious process, isn't it? And it's because we don't have any structure yet in our implementation. Is this a binary search tree? Do we have any restrictions saying that everything over here is greater and everything over here is less? No. So it is a tedious process. I won't finish that process here, but what would it look like? B dot set parent. Who's B's parent? A. B dot set left child. To what? What was it? Left child is D, right child is E. D. So that means I have to move all this stuff up here. Sorry. There we go. So B dot set parent to A, and I didn't call this A. Let me go ahead and capture that. I'll do it like this. A and A. Now I'm regretting how I designed that. Let's go back and make another constructor over here that you handle the creation of the node for me, and then I'll just go ahead and set it. All right, so source constructor using fields, deselect all, and just the, oh no, this is the tree node, sorry. I want the binary tree. So source, generate constructor. Okay, I'm in a class. There we go. Generate constructor using fields, and we'll just do the root here. And that reminds me that I forgot about the size. What would the size be here if you gave me a root element? 1, because you started out with 1 element. And if you gave me the tree root node as the element, then the size would also be 1. Anytime we insert something, we're going to increment this. Anytime we delete a node, we're going to decrement this. Again, we're not there yet. And make this public. Right? And in fact, at this point, I'm going to go ahead and make that one call the other one. Actually, I'll go ahead and go with this root. Nope, the other way around. Right? If you give me a root item, I'm going to go ahead and pass that off. No, I'm going to have to write code to do that. Forget it. Never mind. Let's just go ahead and get this tedious task done now. All right. So instead of A, we're going to go ahead and pass in A, the tree node, instead of the string. Right, there we go. B dot set right child. Now I forget what the right child was. E. All right. That takes care of B. Right. What about C dot set parent? Oops. C dot set parent to A. Remember what it looks like. C's parent is going to be A. C's left child is not going to be anything, and then C's right child is going to be F. Right. C's left child. Ooh, I wonder what we're going to do there. Set right child to be F. What should we do with that if there's no child? Yeah, what could I set it to? What's missing in Java? No. But actually, that was the default, so I don't need to do that at all. That tells me maybe I should be going back to my tree node here and putting in some convenience functions. For example, public boolean has parent. Right. Public boolean has left child. Public boolean has right child, has left child. We did this with a linked list, didn't we? Has next, right? Has previous, if you wanted to do it that way, right child. How would we end up doing this? How do I know if you have a right child or not? Return this dot right child. If it's not equal to null, then it has a right child. If it is equal to null, then it does not, right? And so left child. What about a parent? Same logic here, but what is the one node that does not have a parent? The root. maybe another convenience function here. Public Boolean is root. Return, do I have my own parent? This dot has parent. Oh, it has parent. If that's false, then I am the root. If it's true, then I am not the root. So, what should I return? Not has parent. Right? If I do not have the parent, then I am the root. Right? Nice convenience functions for the future here. Right? And I can say, well, do you have a left child? If so, set it or do something with it. Right? I'm not going to go through the rest of this because of time, and also it's just me typing a bunch of stuff, and I'll have a much better example later on anyway. Okay. But you can see that building this topology of this tree is rather tedious. What if we were to make it a full binary search tree? Right? How would it work to insert an element? How would it work to search for an element, et cetera, et cetera, et cetera? And that's where we'll pick it up next time.